In a communication channel, any communication device when connected, you will find that the quality of the signal is very important and the noise in the channel plays an important role. So while communicating a signal, let's see what happens on the inner side, the data rate and the noise, how they are taken care of. So we will see the different digital modulation techniques which are used internally as a baseband signal, and then before transmission how the modulation takes place and then the signal is transmitted. So to study different modulation techniques, first we will see what is binary phase shift keying or known as BPSK. The BPSK signal when transmitted is a sinusoidal signal which has either 0 degrees or 180 degrees phase shift as per the input message signal given. Now this input message signal which is given can be an audio signal, a video, bit, number of bits 0, 1, data, anything, but the input is taken in a digital format, and if the input is not in the digital format, either if it is in audio or video form, then you need to have some scheme to convert it into digital, and then that digital data is used for modulation purpose. Now when we see a carrier, it is a sinusoidal signal with amplitude A. Now in general, if you want to indicate the signal, if you want to write down the equation for a sinusoidal signal, it is given by PS is equal to half A square, where PS is the power in a signal and half A square, A is the amplitude. So the amplitude of the signal can be given by under root of 2 PS. Now this amplitude is the amplitude of the carrier, and actually in the whole of these modulation techniques we are nowhere concerned with the amplitude. The only interest or the information is there in the phase. So we are interested only in the phase of the BPSK signal and not the amplitude. Now to get the BPSK signal, we need a transmission and reception. So we will just see the equations. Basically a transmitted signal is either VBPSK T, which is given by, which is equal to under root of 2 PS cos of omega 0 t, and this can be also written down as VBPSK T is equal to under root of 2 PS, which is the amplitude, cos of omega 0 t plus pi will be another signal representation for another input bit. So for example, if 1 is the input, you represent the signal by under root of 2 PS cos of omega 0 t, and if 0 is the input, you have a phase shift of 180 degrees, so it will be under root of 2 PS cos of omega 0 t plus pi, where under root 2 PS is the amplitude. So your BPSK signal in general can be written down as B of t under root of 2 PS cos of omega 0 t, where B of t can be plus 1 or B of t can be minus 1. So in general, if you want to write down the BPSK signal, then it can be B of t under root of 2 PS cos of omega 0 t. Now to talk about a transmission. So this simply you have a modulator block to which the input given is your baseband signal, 1 or 0 message signal is given as the input, and another input is the carrier which is cos of omega 0 t. So the balanced modulator output is going to be the signal which is a BPSK signal, and it is the product of these two, which is given by B of t under root of 2 PS cos of omega 0 t. Now this input is given to the receiver, wherein it passes through the channel and the signal is received. When the signal passes through the channel, the receiver receives that signal as under root of 2 PS cos of omega 0 t plus phi, because it is assumed that the signal which is transmitted is going to undergo some phase change because of the noise which is present in the channel. Now this received signal is given to the squarer circuit. Now this square error device, the block diagram is shown wherein the very first block, it is a square law device where it is going to square the incoming signal. So a squarer is used and the output of the square law device is cos square omega 0 t plus phi. Now this output is given to the band pass filter, which is tuned to F0, and there the DC level is filtered out, and the output of the band pass filter is given by cos 2 omega t plus phi. This signal now goes to the frequency divider where we want to retrieve the carrier actually. So this function of a receiver is to retrieve the carrier and also to retrieve the baseband signal, which is the information signal which we had given as an input at the transmission side. So the frequency divider is going to bring down the signal, or it is going to recover the carrier as cos of omega 0 t plus phi. The frequency divider, basically it is composed of flip-flop. It will have flip-flop and also it will have narrow band filters tuned to F0. So this regenerates the carrier, which is cos of omega 0 t plus phi. Now this retrieved carrier is given as an input to the synchronous demodulator, to which another input is again the received signal. Now the equation for the received signal is under root of 2 ps b of t cos of omega 0 t plus phi, which is multiplied by now the retrieved carrier, which is cos of omega 0 t plus phi. So when you multiply this to the synchronous demodulator, the output of that is going to be b of t under root of 2 ps cos square omega 0 t plus phi. Now this goes as an input to the integrator and bit synchronizer. Now integrator is a circuit wherein you have a switch which is named as SC. So this switch closes temporarily and it monitors the bit duration. So this switch closes exactly where the bit duration ends. So that the capacitor, integrator capacitor is discharged totally, and now the integrator is ready for the new bit to come in. So this capacitor charges for every bit duration. The capacitor will start charging and it will discharge at the end of the bit duration. So this SC monitors the TB or the bit duration of the incoming bit. So each individual bit will be defined or monitored separately without considering what was previously 1 or 0. So bit synchronizer is going to control the switch SS. Now this is a sampling switch which will exactly monitor the charge of the capacitor before dumping. So SC closes and the capacitor discharges, that means it dumps the total charge. So just the moment before this, the SS is going to monitor how much is the charge across the capacitor, and based on that the decision will be made whether the input incoming bit was 1 or 0. And in this way we see that the demodulator demodulates the incoming data and decides whether the incoming signal given was 1 or 0. Now if we see the output equation of the integrator, here we can just see the equations and related to all these blocks. So now we have seen how the blocks operate and what is the output and how the demodulation, how the carrier recovery and bit recovery is done at the output of the demodulator. So this represents the PSD of a BPSK signal. Now the signal space representation of a BPSK signal, if we want to find out the distance between the signal points, then that D, it is given by D is equal to 2 under root of PSTB, where PSTB is nothing but bit energy. So also you can write down as 2 under root of EB. So you will see that the geometrical representation of the signal points of BPSK signal is given as shown in the figure.